Okay, so let's go ahead and get started with today's lecture, which starts here, which is chemical kinetics continued, right? And I was telling everybody to get comfortable because we're going to do our lab in here too. Um, and so I might go into lab a little bit explaining about chemical kinetics because you'll need to know how to do this stuff for the lab report and the lab data that you collected on Wednesday. So last Monday, we were talking about this reaction here, right? The one between ammonia and nitrite, if you recall, right? In the first three reactions, we changed the concentration of one of the reactants, in this case ammonia, and we saw that as we doubled the concentration of ammonia here from 0.01 to zero point 0.2 to zero point 0.4, the rate also doubled here. See, we have on the order of 5, and then 10, and then 20, right? And then on the other side of the equation, not the other side of the equation, sorry, in the last three reactions, this time we kept the ammonia concentration, we kept the ammonia concentration constant, and now we doubled the nitrite concentration, right? So here we're going from 0.0202 to 0.0404 to 0.0808, and as we did that, we saw the rate double as well, right? From 10 to 20 to 40, right? We see that trend right there, okay? And so when we take a look at the whole thing, right? Experiments 1 through 3, how it affects the rate, how ammonia affects the rate, the concentration of ammonia affects the rate, and experiments 4 through 6, how it affects the rate for nitrate concentration, right? We find out then that the rate law is actually uh, 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 first order for both of them, right? Because remember what I said on Monday, when you have a reaction, when you have a reaction that is when you double the concentration and the rate doubles, that's called a first order reaction, right? And so we know then that remember that this equation right here actually comes from this rate law, general rate law equation here. Rate equals K concentration of A, and then X there, and then B, and Y there, right? So in this case, the ammonia is the A and the nitrite is the B, right? Is the B, okay? And then our order of reaction is the X and the Y, right? Is the X and the Y. And since when we looked at the data, right? When we looked at the data on the previous slide, we saw that doubling the concentration of ammonia doubles the reaction rate, and then doubling the concentration of nitrite doubles the reaction rate too, right? That's called a first order reaction, right? And since the X and the Y are the orders of the reaction, by the way, RXN is an abbreviation for reaction, right? Then we know that both X equals 1 and Y equals 1 for first order, right? For first order. And so this Y goes here, this X goes up here, and then when you look at the actual rate law, you don't see any numbers there, right? Because when there's not a number there for the exponent, what do you assume it is? 1, right? So that's a first order reaction. And just as a quick review, right, from last Monday, if you double the concentration and it quadruples the rate, that's a second order reaction, right? But for this one, we have a first order reaction, okay? So looking at the same data again, right? Looking at the same data again, let's talk a little bit more about the rate law, okay? When we look at this reaction overall, we knew already that just from the previous slide, right, that the ammonia concentration or the rate with respect to the ammonia concentration is order 1, and the rate with respect to the nitrite concentration is also order 1, right? So a question might be asked in which, what happens when you make it an overall, like the entire, what is the overall rate reaction order, right? Well, it's quite easy. All you do is you add the first one to the second one. And since both of these are 1, 1 plus 1 equals 2, right? So the overall reaction order here is what? Order 2, or second order, right? Does that make sense? Right? Anybody lost? Everybody got that so far? Right? Huh? Who said no? What's wrong? Yeah, yeah. So remember from the previous slide, I said that the order of the reaction with respect to to ammonia was one, right? There was a one right there. Imagine that there's a one up here, and then also there's a one here too because the reaction with respect to nitrite is also one, right? Because when you either double the concentration of the nitrite or double the concentration of the ammonia, right? You get a double in the rate of the reaction, right? So that's where those ones come from. But then the question is then what is the order, right? What is the overall reaction order, right? The overall reaction order, this line right here. Well, you find the overall reaction order by just adding the one plus the one, and that's how you get two. And so the overall reaction order is second order. Does that make sense?
I'm trying to understand what the reaction order is. Like,
It tells you the reaction order tells you that one thing, right? It tells you whether or not doubling concentration quadruples the rate or doubling concentration doubles the rate, right? So in this particular reaction right here, when you double the concentration of either one of the reactants, it doubles the rate. So that's why it's order one, right? But if you double the concentration and it quadruples the rate, that's order two. Does that make sense?
then the overall is
The combination of both of them together. Both, yeah, the overall is two because you're adding the rate from the one reactant to the rate of the other reactant. And the reason why it's confusing to you is because you didn't see us go through on Monday the entire, going each one individually. You know what I mean?
yeah, like you need to watch it.
Yeah. What's up? Say again? Yeah, then the overall reaction order would be three. Yeah. That's rare, but it's possible.
Are they usually the same?
No, it depends on. So that's the one thing that we talked about on Monday. It's based on the reaction stoichiometry, right? What the coefficients are in front of each of the reactants, right? And so when we did this reaction, it was a one-to-one for everything in there, right? All right, everybody got it? Shall I move on? Right? We're just rehashing what we did on Monday right now. So if you were here, right? So here we go. Here's your first question. Yeah, there's such thing as a zeroth order, right? Zeroth order, we'll get to that later today, but zeroth order is when you double the reaction rate and then nothing happens. No change in the I forgot already. No change in the rate. No, not necessarily. Don't think about it like in terms of like kinetics is kind of its own mathematical thing. So unless I say something, because you're going to confuse neutral with like making like a neutral reaction, like neutralizing reaction. Yeah. It's not the same thing. Okay. Yeah, it's not the same thing. All right, so let's see here. We just talked about the reaction order for the overall reaction order for the I lost my train of thought again. The overall reaction order for the ammonia and nitrite reaction. So let's see how people are answering.
That's what it's talking about.
Yeah, the previous slide, right? Oh, I'm still looking for the actual question. Ah, here's overall reaction order. How many people are in here today? Wow, is everybody here today? No. Except for Naraya, which she told me she wasn't going to be here. So, 10, 6, 11. There's 11 of you today. We're waiting for one person. Une person. Okay, there we go. All right, so let's see how everybody answered. This is one of those questions where I literally said it right before the question what the answer was, and I'm glad to see that the vast majority of you got that correct. The reaction order, overall reaction order for the reaction we just talked about is C, second order, right? And the reason why it's second order is because when you look at this guy right here, this previous slide right here, right, we have a reaction order with respect to ammonia as being one, and then, so first order, and then a nitrite reaction order of 1 as well, or first order. A first order plus a first order makes a what? A second order, right? First order plus a first order makes a second order, right? 1 plus 1 equals 2. So we can also find out what K is too. We can figure out what K is now with some concentrations, okay? But the rate constant is temperature dependent, is a temperature dependent quantity, and we'll get to that in just a sec. So here's some other reactions here where it's not a 1-to-1 ratio, right? And so you get different reaction orders. It's not necessarily always related to the balanced equation, right? It's not always necessarily related to the balanced equation, but sorry, I'm getting like important emails. It's crazy. Okay. Um, well, we have this reaction here where we have dinitrogen pentoxide, and it decomposes down into nitrogen dioxide and oxygen right here. Right, we do have a 2 here and a 4 here, but the reaction rate is still just first order, right, for that decomposition, right? Here again, we have hydrogen and iodine becoming hydrogen iodide, still first order right there too, right? And then this one right here, right, looks like it's all 1-to-1, but we have a half order reaction order right there, right? And don't worry, we're not going to deal with half orders right now, so don't worry about that. We're only going to be doing 0, first, and second order. But it's just up here to show you that you can have all kinds of different reaction orders based on many things. One of them is being the coefficients, as I showed you in that previous, when we were going back over that little a, big A plus little b plus little b, that thing right there. So anyway, the reaction order is absolutely dependent on the rate you get when you actually do the experiment itself. Okay. And it's not always going to be the same as the coefficients. All right, so what is the relative value of K then? Well, the rate constant, K is the rate constant, right? And it's often used to determine the relative reaction. So when you have a rate constant that's on the order of 10 to the ninth, which is a super big number, right, or higher, the reaction is very fast, right? And then for reactions that are below 10 to the ninth, those are slower reactions. And so a lot of the reactions we talk about in like your body, like enzymes and stuff like that, that are doing your metabolism and all that stuff, doing electron transport and TCA and all that stuff, right? That's all, and all the ones that are in there that are enzyme catalyzed work really, really fast. Okay, they work really, really fast. So let's first talk about first order reactions. Okay, here I have methyl isonitrile, and it becomes acetonitrile. They look almost exactly the same, don't they? They look almost exactly the same. Well, in this particular reaction, some rates depend only on the reactant of the first power, right? And for the first order reactions, the rate law becomes this, right? Where rate equals the rate constant, or K, times the concentration of A, right? So notice it's a first order reaction, and what is the coefficient there? It's 1, right? So the conversion of methyl isonitrile to acetonitrile is first order reaction, okay? Well, how do we come up with that kind of thing? How do we determine these kinds of things, okay? So, it's gonna get math heavy now, right? If we know that the rate equals K times the concentration, right, of A, and then we also know that the rate equals the change in the concentration of A divided by the change in the time with a minus sign, right? Remember, this is called the differential rate law, right? Differential rate law. We can then make it so that K times A here is equal to the differential rate law. Does that make sense? Okay. So basically what you have here is you have the rate law, right? Just the general rate law is equal to the differential rate law for a first order reaction. Okay. You can then rearrange this a little bit, right? So you can get the K, the constant, and the temperature by itself, right? You can rearrange this a little bit to do that, right? It's easy to do that if you need to know, right? All you have to do is multiply both sides by by the change in time, right? Did everybody see that? Do you want me to show you? If you multiply both sides by the change in time, like that, right? What you end up with is K minus K. Actually, let me do that again. Let's say we multiply both sides by the negative change in time, actually. Okay. And so that makes it so that you have negative K times the change in time equals the change in A change in A. So we've gotten rid of this because we canceled that out, right? And we get rid of those minus signs because we canceled those out because the two minuses make a positive, right? And then on and then let's see here. Oh, I forgot this part right here. Let me write this in again. Negative K A change in time. There we go. Okay, so that's what it looks like when you multiply both sides by negative change in time, right? And then all you have to do now is divide both sides by by the concentration of A. Dang, that's tiny. I'm just going to write that again. Let me erase that and write that again. That's really tiny. I can't even get my finger in there. My pen in there. I mean, it's a good thing I'm not using my finger. That would be worse. Yeah, 1 second. Hold on 1 second. I'm gonna write it bigger on the screen. Actually, I get messed up on the chalkboard, so I'm just gonna write it on the screen. Where's my mouse at? I can't even find my mouse. Oh, there it is. Do not keep this stuff, and then go back to this. There we go. Okay, so let's do that again. I apologize for that. The first thing we have to do is multiply both sides. Dagnammit. I always forget to make it bright. Pen. There we go. So the first thing we do is we multiply both sides, right, by negative change in t. Yes, over 1. Well, negative change in t is the same thing as saying negative change in t over 1, right? So because the numerator is just a regular number. Okay, so that does two things. We cancel out the negative change in time there with the negative change in time here, right? And then it also multiplies to this here, okay? So now what we have when we get that done is we get the negative change in time over here, right? And then K concentration A equals just the change in the concentration of A, right? Everybody got that so far? Okay. And then all you have to do now is divide both sides by the concentration of A. And the concentration of A, like that, right? So that actually cancels out this, like that, right? And that's what we get to here. That's what we have here. You see how this now looks like this? Anybody confused? Right? I'm getting there. I'm getting there. Okay, so we cancel that out, and now we get this equation here, right? And now we have to do an integral. Okay, does anybody remember how to do an integral? So when we get this here, right, we need to integrate this by taking the natural log of this, right? But there's a special little rule, if you remember from calculus, called the natural log, the natural log quotient rule, where it says that um, anything that's ln, right, ln x divided by y, whoops, x divided by y, right, like that, equals ln x plus ln y. Okay, that's called the, oh, sorry, not plus, minus ln y, right? That's called the quotient law, right? The quotient rule for logarithms, okay? And so the reason why usually you see it as lowercase ln like this, right? But when you look on your calculator, it's an uppercase ln. That's why I put it as uppercase for you, right?
Yeah, because that looks like IN.
That also does look like IN too. So that's why I wrote it out as big L. So when you get that right there, right? All that really means is that you can take this entire term right here, right? And turn it into this. Turn it into that. Okay? So what you get then is when you use the quotient rule to do that natural log, the integration, right? You get this, right? That's what you get. So notice now it's the positive a ln a here equals the negative kt plus the ln of the a, right? So that comes from the quotient law. And the reason why we even did this, or quotient rule, the reason why we did this is because this is called the integral rate law, right? This is called the integrated rate law right here. Compare that to doing the differential rate law, which is what we had up here, right? Where you had to have all this the change and stuff right here. This is called the differential rate law. Compared to that, which is the integral rate law, integrated rate law, and you can see how you can just plug things in, right? And the coolest part about doing that is that if you put y equals mx plus b here, which is the line, the equation of a line, you can see how the natural log of the concentration of A is the y-intercept, right? I'm sorry, not the y-intercept, the y value, right? The negative rate constant is the slope, right? And then the t here is the time, which is x, right? And then the y-intercept is the natural log of the initial concentration of A, right? And that has a lot of implications because that means you can graph this now, which is what you'll be doing in lab today. You can graph that now. Yeah, man. Yeah.
You said that this one is the integral rate law.
Yes. Yes.
Integral.
Yes. Integrated rate law.
Oh, integrated.
I was saying you have to take the integral of it, but the law is called the integrated rate law. Yeah, no problem. Integrated rate law. See, I told you guys on Monday we're going to be doing a lot of math. So, because we've moved from the conceptual part of chemistry now to the mathematical part of chemistry, and so that's the next few chapters we have. The chemical kinetics, solution equilibria, acid-base equilibria, and thermodynamics. So we're doing a bunch of math now, right? So what that means then, right, is that it means that the plot of ln A, right, the natural log of the concentration of A versus time is linear, right? So if you were to take all your data that you took on Monday, right, and made it so you did the natural log of all that data, and you plotted it against how much time for each spot, right, for each reaction you did, not each reaction, sorry, each data point you took, right, and it comes out as a straight line, it means your reaction is first order. Does that make sense? Right? Does that make sense? All right. So in respect to the first order reactions, the plot of ln A versus time is what? And if it makes you feel any better, I'm not going to make you go through and do any kind of like derivation of the integrated rate laws like I just did on any exam. I was just showing you how we got there. Does that make sense? But I could be a real, butthole and put one on the written part of the exam. Please derive the integrated rate law from the differential rate law, right? for a first order reaction. What if I did that? Would that be bad?
Yes.
Would that be bad on the written part of the exam?